Finding a regression function or solving a regression problem requires solving a variety of problems. So what are those problems? Well, we need to talk about what we want for our choice of model. The first thing we need to resolve here is the choice of our model. Now, you'll see in a second that all of these quote-unquote problems they're gonna be very interrelated. But the idea here is that if we've got a function f that's going to model our data, we need to figure out what form it takes. Is it linear? Is it polynomial? Is it nonlinear? Is it non-parametric? Right? We need to figure out what relationship we want to use to model our data. The key idea here is that the model defines the space of functions we're willing to consider. If we use models that are too simple, we're going to have the benefit that they're interpretable and computationally efficient, but they may underfit the data. Conversely, if we go with a more complex model, we can better fit the data, but we risk overfitting the model. The next choice we need to make is of our model parameters. So let's call this finding good parameters. So this isn't a problem particularly, but obviously we want to find the best parameters that we can. So once we've chosen the model structure, we need to determine what parameters we're going to use. And we want to find the ones that obviously make the model fit the data well. This typically means minimizing some sort of loss function or maximizing some sort of likelihood. Now, the challenges we face here are that the optimization may be non-convex, which give us maybe many local minima, or this may require regularization or constraints to prevent overfitting. So there's some things that we need to decide here before we move on. The third thing that we want to deal with, or that we want to note, is overfitting and model selection. Overfitting happens when a model learns noise or random fluctuations in the training data rather than the underlying trend. What results here is that the model performs well in the training data and poorly on any unseen data. So essentially the problem with overfitting is that we've selected a model that's too complex, and that leads to high variance. The reverse problem is if we underfit the model, pick a model that's too simple. This leads to high bias. So model selection really is the process of picking the right model. And the goal is to balance both bias and variance to achieve good generalization performance. Problem number 4. The relationship between the loss function and parameter priors. So this highlights the connection between the frequentist and Bayesian views of learning. In Bayesian regression, the loss function corresponds to assumptions about the likelihood, while regularization terms correspond to priors on parameters. Choosing the right loss function implicitly encodes assumptions about the noise in parameter distributions. So we need to be careful here about how we pick our loss function, be it through regularization or some other way, and what impact this has on the assumptions for our model. The fifth thing that we need to really pay attention to here is uncertainty modeling. So in real-world regression, we rarely expect perfect predictions. It's important to quantify uncertainty. How confident are we in a given prediction? Now, there's a lot of different types of uncertainty that we can have. We can have uncertainty due to randomness or noise in the data. We could have uncertainty due to limited data or a lack of knowledge about the model. So we need to figure out how uncertain we are about our outcome, and we need to model that in some way. Being able to quantify uncertainty improves interpretability and decision-making, especially in high-risk domains like finance or medicine. So to summarize, linear regression is not as simple as just taking our data and throwing it into R or Excel or Python. We need to consider the choice of model. So decide on the functional form of F. Are we using linear, nonlinear, kernel, neural nets? What are we doing? Next, we need to find good parameters. We need to optimize these to minimize our loss or maximize our likelihood. This might involve things like gradient descent or least squares. We need to worry about overfitting and model selection. So here there's a balance between model complexity and the fit of the data. We may need to use techniques like cross-validation or regularization here. We need to then deal with the relationship between the loss prior. Connect frequentist and Bayesian views here to determine what relationship the loss function and the parameter priors are going to have. And finally, we want to quantify our confidence in our prediction by doing some uncertainty modeling. So as you can see, a regression problem is quite involved. And you really need to discuss each of these ideas before you publish any of your results.